Hi, this is Mr. Marquetos. In this video, we are going to look at the chain rule. Of all the rules for differentiation that we learned, the chain rule is by far the most powerful. The reason for this is it is the rule that allows us to differentiate composite functions or the composition of two or more functions. And as we will see, a lot of the work in the remainder of Unit 2 has its basis in the chain rule. So before we even do any calculus, what we need to make sure is we really understand composition of functions and seeing functions as the composition of functions. So in number one here, each of the functions h below, there's three of them, are composite functions decompose into two functions f and g, such that h of x is f composed with g of x, which from our knowledge of composition, we know that means f of g of x. We often think of whatever function's out here, which in this case is f, as the outer function, and whichever function is in here, and it is literally inside of the outer function, so it's kind of easy to see in that way. We call g the inner function. So for a, we have h of x is the cosine squared of x. One really important thing here, and I picked the trig functions in a and b because this really beats people up here. If I look at this function cosine squared x, we could rewrite that as what it actually means, which is the cosine of x all squared. That is how cosine squared x is defined. The other benefit there is it is pretty clear which function is on the inside and what is your outer function, the squaring function. So if I want to make f the outer function and g the inner function, I'm going to say here that f of x would be the squaring function, which is just x squared, and the inner function, g of x, would be cosine x. And if you're not 100% comfortable with that, all you have to do is double check yourself and actually say, okay, so if I take f and I compose it with g, will I get back cosine squared x? So let's be careful with this one. Of course, this means f of g of x. And then, right, we could say that's f of cosine x, because cosine x is g of x. And then all I'm doing is replacing x and f by cosine. So that would be equivalent to cosine x all squared, which of course we always see written as cosine squared x. So I'm not doing any calculus here. All I am doing is trying to make sure that I'm able to see the outer and inner function of a composite function. Let's do that again, a little more detail as well. So in B here, again, I'm picking these trig functions. This time the function h of x is the cosine of x squared. Now, when it's written like that, again, what people mean literally is the cosine of x squared. You may not see parentheses around the argument of your trig function if it is a single term. So it might be helpful to even put those there. And when you do put those there, again, it sort of becomes more clear about which function is the outer function here and which function is the inner function. The outer function here is the cosine function, so we would say that f of x in this case, because again, I'm making f outer, is the cosine of x, and g of x in this case is what's inside, which would be x squared. And again, if I feel a little uncertain about the way I am seeing that, I can check pretty quickly. I just have to make sure that f of g of x gives me back, in this case, h of x. So that would be f of x squared. And then I am just placing x squared in for x in f. So that would give me literally cosine x squared. And maybe we won't go crazy with c, but let's also complete it. So we got h of x is the square root of 7x squared plus 9. I do think, depending on the type of functions you are working with, it is more visually clear who is inside, who is outside. I think people would say that about the function h of x in part C here. So the outer function is the square root function. So f would be the square rooting function, the square root of x, and g would simply just be what's underneath that. It's incredibly important that I can look at these functions and think about them as composite functions, because if I do not do that, if I do not identify who is the outer and who is the inner function, it's going to make the chain rule difficult to use. It's already got a bit of a learning curve to it, so we have to be careful, but composite functions, it's a big thing in calculus. So what is the chain rule? Because that is today. So we have two functions, f and g, and they're differentiable functions, meaning like their derivatives are defined at all values of x. So look what we have here, because really this is just, that's the rule. That is the chain rule. So you're ddxing, right? And of course, ddx in calculus means take the derivative of whatever's inside there. So you have the derivative of f of g of x. This is a composite function. If you are differentiating a composite function, you need what is called the chain rule. On the other side, you see what you get. It's f prime of g of x times g prime of x. So I do sort of have like a internal monologue with myself when I think about how am I using the chain rule as I'm working some computation. So I'm thinking, of course, as f as the outer function, it's outside, and then g as the inner function, it's inside. And again, here's kind of like my monologue that goes on in my mind. So what's happening first? I differentiate the outer function first while leaving the inner function alone. That part of my, monologue to myself, inner monologue, whatever you want to call it, that is this portion of the chain rule. You differentiate the outer function, which is f, so you get f prime, but you leave the inner function alone. You see inside it's just g. I didn't do anything to it. It's still just g of x. So you're differentiating the outer function, you're leaving the inner function alone. Then there's some more to this, so we have some more English to look at. Then multiply by the derivative of the inner function. That's this. The inner function is g. So all I'm doing there is multiplying by the derivative of g prime. It's like even just looking at that definition of the chain rule, it's pretty hard to understand without looking at a few different examples of this. And one thing to keep in mind with all these rules we are learning over the past couple of weeks, every new rule you learn can be used in conjunction with all the other rules you know. And I think how these rules integrate and work with each other is part of the challenge for sure. Let's do a little chain rule differentiation here, and maybe again, always good to review. Can you find the equation of a tangent line? Because Lord knows tangent lines are half of calculus in some sense. So this function I gave you, y equals 7x squared plus 9, that is actually the one from C. So we already kind of identified who is outside and who is inside. We know that if you want to construct the equation of the tangent line, you need two pieces of information. You need the slope of this function at x equals 4. That requires differentiation. And you also need the point of contact, which is really just the point on the graph when x is 4. You could find either one of those things first. So I say, why don't we get that out of the way, because that's maybe the easier thing, right? So when x is 4, y is square root 7 times 4 squared plus 9. And that would be y equal to the square root of, that would be 121. Square root of that is 11. So our point of contact is 4 comma 11. That's, of course, the easier part. It does not revolve or require, I should say, calculus. Now, let's be careful with sort of my second thing that I need, which is the slope of the tangent line. The first thing I'm going to do, as I do when I differentiate any square root function, is I think about the square root as something as a power, right, to the half power. I need to do that still here, but now when I'm looking at this, I'm seeing that the outer function is the square root or something to the half power, and the inner function is 7x squared plus 9. Try to follow this here. This is pretty, you got to be careful. So I'm finding the derivative. We've seen that if the name of the function is y, a lot of times we call the derivative dy dx. So first part here, I am differentiating the outer function while leaving the inner function alone. The outer function is x to the half, right? So if you differentiated that, you would get 1/2 x to the minus 1/2. I think we're all getting very comfortable with that. That's what happens here, except you don't have x, you have 7x squared plus 9. Look what I'm about to put down, how it's very similar to that. It's just that the inside is staying put. So it would be 1/2. Leave what's inside alone, 7x squared plus 9 to the minus 1/2. I'm not done, by the way, but I'm just trying to like narrow in on this idea here. You differentiated the outer part, the function being raised to a half, right? So you have something that looks like this. It's just that the inside has been left as 7x squared plus 9. That is differentiating the outer function while leaving the inner function alone. There is a sort of second component to the chain rule, which is right here. Now I need to multiply by the derivative of the inner function. The inner function here is 7x squared plus 9. That's not hard to differentiate, but putting it all together is pretty tricky. So I'm multiplying by the derivative of what's inside. The derivative of 7x squared is 14x. The derivative of 9 is nothing. That's my derivative. However, I really don't want to leave it like this ever. If it's a mess, it becomes hard to work with. And so I'm going to simplify this. Certainly, I could do half of 14 is 7. And I could bring this downstairs into the basement with the negative exponent. So dy dx would be careful here, you'd have a 7x up in the attic, the numerator. You'd be bringing the 1/2 power down into the basement. And you might even change that straight up to square root 7x squared plus 9. If you left it to the 1/2, that would not be wrong in any way. But realize now that I have my derivative and it's simplified, I'm going to want to use it to get the slope at x equals 4. None of that is new. Here's where the new stuff is in this first question. It's really just right here. That is getting the derivative using the chain rule. Remember too, if I use dy dx as my derivative notation, the way we say that, hey, I'm going to plug x is 4 in is by putting that bar equals x is 4. X equals 4. That just means I'm plugging in x is 4 into this expression. You know, you might say, well, why don't I just put like 4 in there? It's just not the notation. So there's other reasons for that. We'll see as the year moves along. So I got 7 times 4 over square root 7 times 4 squared plus 9. So that would be 28 over square root 121, which would be 28 over 11. That's your slope. It's a number, somewhere in between 2 and 3, closer to 3, but that's my slope. And so the last thing I'm doing there is just taking my slope, which is 28 over 11, and my point of contact, which I found in red, that's 4 comma 11, and I'm taking those two pieces of information, and I'm throwing it into point slope. So y minus y1 equals m 28 over 11 times x minus x1. I'm leaving it like that because I get full credit leaving it in point slope form. But again, here is where the new thing happened, using the chain rule. So let's take a peek at some different examples and really just focusing in on the process of differentiating using the chain rule. Once you get it, it's really not any worse than any of the other rules. However, I would say it's a little harder to get the chain rule compared to, let's say, product rule, quotient rule, power rule, things like that. For A, before I do a lick of calculus, I'm going to rewrite that expression. Sometimes rewriting things before you do calculus not only is what allows you to do it, but makes your life a lot better. So this would be the 1/4 power. So you'd have something cubed to the 1/4. So I hope we're comfortable maybe just going right here, 3/4 power. That's perfectly fine in terms of somebody saying you're showing enough work. But I don't want to write too many steps because I haven't even attempted my calculus yet. So, okay, finding the derivative. So it's dy dx. 2 is a multiplicative constant, so it's going to sit there. That's actually an old rule you already know, but it's appearing here. Okay, I'm differentiating the thing on the outside, which is raising something to the 3/4, while I leave what's inside alone. So the 3/4 comes down because I'm using the power rule. That's all I'm doing. It's just that I'm leaving that inner expression intact. Oops, and I forgot it should be minus 1/4. 3/4 minus 1 is minus 1/4. So, okay, now I'm not done, of course. I need to multiply by the derivative of the inside. This process that happened right here, that is only this part of the chain rule. You just need to multiply by the derivative of what's sitting inside. What's inside is 9 minus x squared. The derivative of 9 is 0. The derivative of x squared or minus x squared is minus 2x. I'm done with calculus, but it's really not a great idea to leave it like that because, one, on multiple choice, they're going to ask you to simplify it to pick the right answer. And on free response, I would have to do something with this, and leaving it like that is not going to help me a lot. So let's see. You're dividing by 4, but then you're multiplying by 2 and 2. So that all goes. You have a 3 and a minus x. So in the numerator, you'd have a minus 3x. This you can bring down. Again, if you leave it, if I left it like this, that's nothing, that's perfectly fine. I would say that's simplified. You just may see somebody change that in the bottom to 4th root 9 minus x squared. I think here it is a little bit clearer in some way who's inside versus who's outside compared to if we look at b here. So I got f of x equals e to the square root x. Again, maybe just, especially right now, I'm thinking about, okay, square root x, maybe I'm writing that as something to the 1/2 power. Here, be careful, and maybe we should even make this note here. The outer function is e to the x. The inner function is x to the 1/2. Be very careful because, like I said, some functions, it's a little harder to see for some reason who's inside, who's outside. But once I recognize that, it should be no problem. So f prime of x, the derivative of f of x. So it's differentiate the outer function while leaving what's inside alone. What is the derivative of e to the x? It's e to the x. Actually, the derivative of e to the something is e to the something times, we'll get to that in a second. So the derivative of e to the x to the 1/2 is e to the x to the 1/2. That is actually me differentiating the outer function while leaving the inner function alone. But then I have to multiply. I have to multiply by the derivative of the inner function. The inner function is x to the 1/2. And we differentiate that just using the power rule. So you'd have 1/2 x to the minus 1/2. And again, I would clean that up. I think, we're getting to the stage where we should be getting more and more comfortable with rewriting an expression quickly without showing, maybe 3 or 4 intermediate steps. Obviously, work needs to be there, but I don't know, in this problem here, I would probably go like this. So you have e to the x to the 1/2. Probably put that back as e to the square root x. And then this, right, you can rewrite that as 1 over 2 square root x. So that would be in the basement. And I'm simplified already. Again, it's not like I'm doing a lot of work here to get the derivative. But I think conceptually, it is a bit demanding at first, but like anything else, if you practice it, it will get easy. Let's look at C here. Maybe we'll work down here. So this one, again, it shouldn't be too bad. I think here, again, it's kind of clear who is outside and who is inside. The sine function would be the outer function here. The inner function would be the cosine function. Again, sometimes it's just easier to see these things. G prime, g prime of x would be, okay, again, this is the mantra, the inner monologue that happens. You differentiate the outer function. What is the outer function here? Sine. You differentiate the outer function while leaving the inner function alone. The derivative of sine is cosine, and I'm leaving the inside alone. I'm not done, but that's sort of the first step in the process. So you get cosine of cosine x times the derivative of the inner function. The derivative of cosine is negative sine. That is my derivative. There's really not much I can do either here in terms of cleaning up, because like you can't like multiply these things. I would probably have it written like this, and you'd probably see it written like this on a multiple choice as well. Minus sine x times cosine of cosine x. Not much I can do there in terms of simplifying. And then finally, d here, we have, again, another composite function, h of t this time. So, we might need a little room for this one. So I got h of t is t cubed over, t squared over t cubed plus 2 all squared. Okay, again, not terrible in terms of trying to see that outer and inner function. The outer function is something squared. Again, maybe it's not bad to even say this here. What's outer is something squared. What's inner is t squared over t cubed plus 2. We can try to do different things here to maybe like help us out. What I would say though is let's not get too fancy right now, because if you try to get too fancy with, trying to do something with that expression before you differentiate, I think you're going to cause yourself some problems, especially this early on. You want to focus on the basics. So h prime of t. So I am differentiating the outer function while leaving the inner function alone. So let me fix my equal sign here. So the 2 comes down in front, right? And it would be like 2 minus 1. I'm going to leave it as just to the first. Actually, I'm not going to write anything, right? And then, but you see, I haven't touched what's inside. If you kind of, maybe if I put the 1 there and you kind of cover this up and you put a t, you see you're just getting what you differentiate when you do t squared. It's just that inside is something more complex. Here's a fun thing. So you took the derivative of the outer function while leaving the inner function alone. Now you have to multiply by the derivative of the inner function, which is a quotient and requires the quotient rule. Taking derivatives can be kind of a messy process depending on what you're dealing with. So I'm going to put a nice big fraction bar here because now I'm using the quotient rule. So it's low d high, the derivative of t squared is 2t, minus low d high minus high. You see I have to do this or else I would get it wrong. Minus high d low. The derivative of t cubed plus 2 is 3t squared. Square the bottom, and away we go. So that would be my derivative. That would put me at the place where I've actually finished my calculus. To answer your question that's right in your mind right now, yes, I would be expected to, and there are quite a few situations that I may need to clean something like this up. So let's make sure we can do that. By the way, this is to the first power, so like you could kind of say like, the power's irrelevant there, right? Anything to the first is itself, so I'm not even going to write that. So I have 2 times t squared over t cubed plus 2. The bottom here, do not expand this. That would be a huge mistake. Leave it alone. The top, let's clean it up though. I can distribute here and I can distribute the negative t squared there. So, I can do some things here. 2t to the 4th plus 4t. I think I needed a bigger fraction bar, unfortunately. This would be minus, 3t to the 4th? Feel like I'm doing something silly, but I think I'm good. Okay? And I'm trying not to jump steps here because I want you to see, like, it's actually not that bad to simplify this, but don't get, like, crazy because then you mess it up. And if you have to use this for something, everything you do after this would be wrong. So these two combine. So I'll do that. So that's minus what? minus t to the fourth plus 4t. Okay, now you're multiplying fractions across, right? So let me just shrink this a bit. I don't want to run over into my space underneath. So I might leave my final answer here for h prime of t. I might leave it like this: 2 times t squared times minus t to the fourth plus 4t. Okay, now the bottom is 1, which whatever. You could think of this being to the first, and this obviously in the last denominator being to the second. So I could think of the product of those being cubed. Now you might say, oh, you could distribute the 2 and the t squared. I could, but if I don't, there's nothing wrong with that. And in fact, there may be very real reason why I prefer to leave it factored, as we will see. But get in that habit of saying to yourself, I'm differentiating the outer function first while leaving the inner function alone, then I'm multiplying by the derivative of the inner function. Before we look at some AP style business here, I want to take a look at a situation like number 4. I find this is the situation that gets one of the situations that get students into a bit of hot water, and hot water just means they get the wrong answer because they're trying to do too much with these rules too early on, I think. So notice with this function in 4, s of t, it is a quotient. However, the numerator is a constant. I'll tell you the truth, nobody really likes doing the quotient rule. It's kind of annoying, right? It's a longer process. It's easy to mess up with the sign in the numerator. Nobody really enjoys doing it. Here is a place where I would say avoiding the quotient rule is good, but no matter how many times I will say this, I'm not telling you not to do the quotient rule. There are plenty of times where you should be using the quotient rule. I'm saying with our new friend, the chain rule, this might be a situation where I don't necessarily do it. So rather than use the quotient rule, rewrite s of t first so that the chain rule could be used. Then use the chain rule to find s prime of t, the derivative. So I'm going to think of what's in the denominator as being to the first, so that when I rewrite it, here's what I'm thinking. I'm thinking about using my laws of exponents. I could say this is 2 times 4 minus 5t minus t squared to the negative 1. The reason I'm doing that now is because now you could think of this as like a composite function. Again, what would be kind of what's cooking on the outside? On the outside, it's like saying you got 2t to the minus 1. On the inside, you have that quadratic polynomial expression. So because I can think about or even rewrite this function as a composite function, or think about it as a composite function this way at least, because technically this is still composite, but I can use the chain rule and avoid the quotient rule. So I'm looking here as I'm about to differentiate. Okay, so maybe down below we'll write down what s prime of t is. So s prime of t. Okay, you're differentiating this outer object here. So it'd be 2, okay, the negative 1 would come down as a coefficient, and then it would be like t to the negative 1 minus 2, right? Or sorry, minus 1. You're taking 1 off the exponent. So it'd be minus 2 up there, which we do mentally. That's what's happening at the moment. It's just you don't have plain old t there. You have this inner expression, which I'm not touching at the moment. I'm just leaving it alone. So here's what I got. I differentiated the outer function while leaving the inner function alone. Please, I am not done. I have to multiply by the inner function, the derivative of 4 minus 5t minus t squared. So that would be, the derivative of 4 is 0. The derivative of minus 5t is minus 5 minus t squared. Its derivative is minus 2t. I would clean this up again. I would not leave it like this. You could think of this binomial being to the first. I might add a little highlight here on these parentheses. They are incredibly important. You're multiplying by the derivative of the inside. The inside's derivative has multiple terms. You need those parentheses there to group them, or else you will end up with, your derivative would be correct, but if I substituted and or tried to simplify it, I may end up with the wrong expression because I haven't grouped those terms. So let's clean this up a little carefully. So this would be minus 2. Then, this is like to the first, right? So I'm just leaving this here as is for the moment. This, I'm going to bring it down into the denominator to make the exponent positive. So 4 minus 5t minus t squared. And to the second, of course, whoopsie. I probably would distribute the negative 2, I guess, right? I mean, what would that be? Positive 10 plus 4t over 4 minus 5t minus t squared, all squared. Lovely stuff. Cool beans. So that is the chain rule, and like I said, we see it a lot. It shows up everywhere. It's in multiple choice. It's in free response. It actually leads to more techniques coming in the following weeks. So one kind of beef up, I guess, from anything like 2, 3, and 4 is it is a fact that the chain rule can be used repeatedly. In fact, you could use it indefinitely, depending on if your function, like how many functions make up that composite function. You may have a function that is the composition of 3 functions, 4 functions, 5 functions. We'll put this here. It's probably easier to understand when we see it in action, but this was in the reading. Let's put it up here anyway. So what would happen if you tried to differentiate f of g of h of x? Besides vomiting and getting nauseous, how would that go? You work your way from the outside in, right? So right now f is outside, everything in here is inside. So I differentiate the outer function. F becomes f prime, but I leave the inner stuff alone. Okay, I got a bit more to do though. I'm working my way in. I'm putting a times, by the way. You're always multiplying when you use the chain rule. I'll tell you why it's called the chain rule in a second. Now I'm looking at this. What do you got to do? You keep doing the same thing. You differentiate the outer function, which is g now, and you leave the inner function alone. So that would be g prime of h of x. Now, right, I work my way in. There is only one function left on the inside. That is like the ultimate inner function here. It's the inner function. The derivative of the inside, the derivative of h, would be h prime. So you could have with 4 functions, 5 functions. We'd also see here the reason that people call this rule the chain rule is that these terms that come out from taking the derivative, they are linked or chained together by multiplication. That is where the rule gets its name from. So that example, they are willing to go up to the composition of 3 functions. They will do it. No more than that. So you will not see the composition of 4 or more functions. So a little multiple choice action here, always fun. D dx of sine cubed of x squared makes you vomit is what? I think before you do any calculus, you should be very clear with what you're looking at here. And, making good use of your parentheses is kind of a big thing here. What does this actually mean? This actually means the sine of x squared cubed. I think if you do not rewrite it that way, or at least mentally think about it that way, you're going to differentiate this expression wrong. So, I mean, we could go what's outer, what's, inner, what's inner, but just look at what you have here, and all you're thinking about is working from the inside out. So what's the outermost thing? Something to the third. How do you take the derivative of something to the third? It's 3, right? Something to the second. So I'm not touching the inside at the moment. So it would be 3 sine of x squared to the second times. I work my way in now. What do I got looking, or what am I looking at there now? It's the sine of x squared. Sine of x squared is still a composite function though, right? Now the outer function is sine and the inner function is x squared. But I keep applying that same rule over and over again. So now, right, I'm differentiating sine, which is cosine, and I'm leaving what's inside of it alone. But still, right, inside it's not just plain old x. If it was, I'd be done. But this is the composition of three functions. So one last time, now I multiply by the derivative of the innermost thing. What's the derivative of x squared? It's 2x. I would be careful here when you pick your choices because, you know, some of them look the same, kind of, sort of. I would carefully clean this up. So 2x times 3, that's 6x. Let's just stick that in front, which actually would eliminate 3 of the choices, I guess, right, based on the way they're written. But, yeah, so sine of x squared, you're going to see somebody write that as sine squared of x squared. That's how it's going to be written, times the cosine of, if you want the parentheses there, you can, kind of thing. And that leaves us with choice E. So I will not get the composition of 4 functions. That is, you know, even a little too much for them. It's not terrible. Can we do this one more like that where it's 3? Just be clear here. If you got an expression with an x in it, and it is anything, God, the highlighter's annoying when it's small. If it is anything but plain old x, meaning positive 1x, you need to be very careful about applying that chain rule. I mean, I don't think you're going to see somebody write this way, but it's kind of like sine of e of minus x. So you can see like who is the most outside, who is kind of in the middle there, and then who is the most inside. The most outer is sine. The most inner is minus x, and sort of in the middle, I guess you could say, is the e to the function, the exponential. Again, we differentiate the thing on the outside. What's the derivative of sine? It is cosine. You do not touch what's inside. So you get e to the minus x. But now I have to multiply by the derivative of this. What we kind of say is that the derivative of e to the anything is e to the anything times the derivative of that anything. So what's the derivative of e to the minus x? It would be e to the minus x, but then now I have to multiply by the derivative of negative x, which is negative 1. It's funky, and I think even like, you know, depending on the type of functions that you're composing, sometimes it feels easier, sometimes it feels harder. So probably see this rewritten this way, minus e to the minus x, and then you have your cosine of e to the minus x. So that would be e again, wouldn't it? Looks like it. Am I good? Yeah, be careful, right? Like, so again, you know, there's only a small difference between d and e. The pluses and minuses here, that you have multiple terms, right? This is actually one term. It's bound by multiplication. That would kind of tell you that B and C are not a possibility. A is just a abuse and misuse of the chain rule. So yeah. Cool beans. So aside from like mechanically doing things, obviously we see that our functions given to us often have some different representations, mainly equations, which we see a lot, but I would say that equally as much we do see graphs and definitely tables. So this is a pretty, I thought this was a tough AP question, especially early on, but might as well not waste any time. So the graph of the function f consisting of 2 line segments is shown in the figure above. Let g be the function given by, they say f, sometimes I remind myself like, yeah, that's f. Let g be the function given by g of x is 2x plus 1, and let h be the function given by h of x is f composed with g of x. Cool beans. Composite function, what is the value of h prime of 1? So the derivative of h at x equals 1. This is by definition a composite function, which means that I must apply the chain rule here. So I'm finding h prime first, of course. Well, maybe we should do something else here based on what they told us. They actually told us what g was, correct? It's 2x plus 1. So maybe let's take a little note here. So h of x, which they're saying is f of g of x, we could say that is f of 2x plus 1, because that's what g is. Okay, and that might make life a little better here. I don't know. We're about to find out when we differentiate. I think what happens here, though, blows people's mind at first. So again, if this like feels weird at first, it's kind of natural to feel strange when you do this. So when you look at this function, who's outside? It's this function called f. That's the outer function. And who's inside? It's 2x plus 1. So when I apply the chain rule, I do not change the way I think about this. I don't change my mantra. If I did, it wouldn't be a mantra. I differentiate the outer function. What is the derivative of f? It's f prime, while leaving the inner function alone. Then I multiply by the derivative of what's inside. What is the derivative of 2x plus 1? Well, the derivative of 2x is 2. The derivative of 1 is nothing. It is 0. Okay, so, I mean, I got h prime of x. Now I need to find h prime of 1. So maybe I'm like, all right, so I actually feel okay. I'm just going to plug in 1. Maybe I'll put the 2 in front, obviously, as a constant. So 2 times f prime of, I don't want to, like, write 100 steps, but I don't want to skip too much here, because this, again, this, I think, feels a little uncomfortable at first. You're like, what are you doing? Anyway, that would be f prime of 3. Okay, so now the answer and the choices are purely numerical. So obviously, if I stop at 2 times f prime of 3, I'm probably not done. So what? Well, you have the graph of f, yes, and here is x is 3. And you actually have these 2 points on the graph, which I think I'm going to need in a minute, right? Like, kind of like, well, we'll see how we're supposed to think about this properly. This is f. What would f prime of 3 be? Maybe let's do this just so I don't, like, get too crazy. What would f prime of 3 be? It is the derivative of this function when x is 3. It is the slope of the tangent line to that curve when x is 3. But guess what? The function, both pieces, but certainly the function at x is 3, is a linear function. So what would the derivative of this function at 3 would actually just be the slope of the line, wouldn't it? That's what the derivative tells us. So when we think about linear functions, you kind of don't use calculus there in that sense. If you want the slope of this line, I mean, just find the slope of the line, right? It's the same all on, at least from 1 to 4 on that interval, it's the same. So f prime of 3, right, would be like y2 minus 2 minus what? y1, which is 4 over x2, 4 minus x1. So that would be negative 6 over 3, which would come out to negative 2. So maybe we'll use a little coloring here. This quantity, f prime of 3, is negative 2. So that would mean that, coming down one more line, f prime of, that's a different red, but that's okay, would be 2 times negative 2. So what would that be? Negative 4. Voila. Yes. Cool. That's a different look, I think, of understanding of calculus. When you get, like, they're mixing and matching representations, graphs, and equations, that is when people, like, start to get a little, okay. And last thing we'll look at in this video is, again, one more AP multiple choice question. As I said when we kind of went over what the chain rule says, all of these rules can be used in conjunction with one another, okay? So when I look at e to the 2x times x cubed plus 1, right, I see a product. So when I'm looking at the product rule, I am thinking about, who is first, who is second. E to the 2x is what's first. X cubed plus 1 would be second. By the way, I would not distribute the e to the 2x. I would actually leave it as it is and apply the product rule. But notice what happens in the middle of the product rule. Again, trippy. So they want f prime of 2. Well, you're not going to get f prime of 2 unless you first find f prime of x. That's not possible, right? So again, I have my mantras, right? So it's first, e to the 2x is first, times the derivative of second. What is the derivative of x cubed plus 1? It's 3x squared. It'd be plus 0 because the derivative of 1 is nothing, but I'm not going to write that, of course, so we're done with that part. But it's first times derivative of second plus second, so x cubed plus 1, times the derivative of first. Be careful here because now when you do the derivative of first, you need the chain rule. That is a composite function, right? Inside is 2x. It is not just e to the x. It is 2x. It's a composite now. So I differentiate the outer function while leaving the inner function alone, right? I get e to the 2x times the derivative of the inner function, 2x, which is just 2. Maybe like this part here, maybe we'll add a little note here. Like, again, I think, this kind of bothers people, right? But if you differentiate e to the 2x, you're getting e to the 2x times the derivative of 2x. I tend to never write this because, one, it's time consuming. It's going to make your work messier. I try my best to get to a place where I can get from, I'm taking the derivative right to here. And it's okay, like, not showing this step is not you, like, showing insufficient amount of work. I try to take the derivatives of little things in my head, like the derivative of 2x is 2. I don't want to write out a separate step for that, right? So that's the product rule. But notice when I used my product rule, when I did d first, I needed the chain rule. So these rules are getting used in conjunction with one another. Do I want to clean this up at all? I don't know, maybe be like 3x squared e to the 2x plus, I don't know, 2e to the 2x times x cubed plus 1. I wouldn't go crazy because it's not too messy. And now what do you want? I don't know why I keep switching colors. You want f prime of 2. So I'm going to put 2 in here, and I think that should give me my answer. So 3 times 2 squared plus e to the 2 times 2. I'm just going to put e to the 4. Plus 2 e to the 2 times 2. I'm just going to put e to the 4. And then it's 2, that's 4. Then it's 2 cubed plus 1. So what do you got here? That would be 12. So you have 12 e to the 4s. This would be in here 9, right? 2 cubed plus 1 times 2 is 18. So I have 18 e to the 4s. Altogether, I have 30 e to the 4s. And my answer is indeed choice D. That is the chain rule. There is some more videos this week on it, and we will actually, in the coming weeks, use the chain rule to develop some additional techniques as well as applications. So it's only the beginning of the chain rule. Hope you're doing well. We'll talk soon. Peace out.